Okay, that's all for this tutorial, but I just want to add another things before I forget. This one is related to one of the question or from the feedbacks there during the first lecture. One of the student asked about which activation function is the best. Actually, is not there's no answer for that. What we have learned is actually is a evolution of activation function. Okay, you can see that I think the one that you can refer is this one. I think you can search through the Google and related to activation function, but one of the article that I like to read is this one. Okay, they actually it's the evolution, meaning that during the initial during the earliest days, when they try to implement the neural network, they start with the what we call as a perceptron algorithm. As you remember the perceptron algorithm, okay, the linear perceptron algorithms is the first one, the first version of the artificial neural network before we can have our recent neural network, which is more advanced and better than the earliest one. And they use this, you can see they use this binary functions there. Okay, they use a binary. It means that it can be 0 or 1. Okay, if you remember that what is the disadvantage of this one? Let's say if you want to find the derivative of this one, of course if you talk about back propagation, you need to have a forward pass, backward pass, and that will involve the derivative of activation function. So if you do derivative of this one, then you just can get a straight line 0, because derivative of this line becomes 0, derivative of constant will become 0. So that's mean if this becomes 0, then imagine that your updater is not moving at all, because the updater is always 0, so it will repeat forever. If you do that's why if we discussed earlier when what is the disadvantage of perceptron algorithm is that it will keep repeating the same it will do the loop forever, because the W is not updated, because the updater is 0. So that is the disadvantage of using step function like this, or the binary function like this. So that's why they try to change it or try to improve it by having another activation function, and then they come up with the linear functions. And against the linear function, what is the advantage is that as you can see here is that you have a fixed derivative like this. So once you have fixed derivative, and what is you can see it explain over here, and then where is it? But yeah, you can see. But when you have a fixed derivative, then that will become the problem. Why? Because okay, you can refer to the discussion over here. Okay, actually it's reasonable, because if you have the derivative produce the fixed number, then it's consider that there's no learning process at all, because your doesn't matter your input value has been changed, or your W have been updated to the new value, but later when you implement a backward pass, you still get the same updater, because of the derivative of this function is always constant. Means that there's no changing at all in term of updater. How is it updated? So the updater is fixed. Okay, let's say just imagine that your alpha is 0.5, and then let's say the updater is the value of the del W13, for example, is 2. So 2 times 0.5 is 1. So each then you will update your W12 there with with value 1, and then next cycle do the back propagation for pass backward fast, you still update your W13 with with value 1, and again 1 during the next iteration is still equal to 1. So the learning process is not happen at all. So that's why by introduce with the linear function is not appropriate way to represent the learning process. Then people try to revise on this one and try to improve on the activation function and replace it with another activation function. Okay, one of it is a sigmoid. With this we have learned it before. Okay, but it's very good, as you can see this. Okay, I forget to mention this blue lines here is represent the value of your f head, or the derivative of this function. I'm sorry, it's not f head, f apostrophe mean derivative of this one, derivative of this orange line is the blue line. Okay, so this one, where is the blue line? The blue line is at this x-axis, so it's always 0. This one is always constant. Then they introduce with the sigmoid function. So sigmoid function is a little bit good and better as compared to the previous one, because you can see that the blue lines there is not fixed, means that they have their own changings there. Okay, so that's good for the learning process, because once the value is at this position, you will update very big value. Once your value is at this particular position, then you will update a little bit small value. So it's good to have that kind of learning up until you converge. Your algorithm going towards the converge or the convex to find the optimum WNB there. Okay, so but there is also disadvantage of this one. So what is the advantage of this one? Is because they find out that since the value of updater is very small, you can see that the maximum number is at this center there, which is the biggest one. Okay, is 0 point something. So so because this is very small, then that will make your backpropagation suffer with what we call as the vanishing gradient. So what is the meaning by the vanishing gradient? You can try to search for this one, this term. What is vanishing gradient? Is actually, roughly speaking, it happened is our in our example here. Okay, the example that I showed before. Yep, this one. Okay. Okay. Yeah. So why I said the vanishing gradient happen here? You realized that? Okay. This is represent the updater for output layer. Okay, you can see the value is 0.04, which can be considered as a very big number in representing as an updater. But what happened at the hidden layer, which is the updater at the hidden layer? Yep, this one. This is the updater at the hidden layer. You can see that the updater at the hidden layer is very small, too small, 0.002, 0.004. The biggest one is this one, 0.044. The rest is 0.003 and 0.005. You can see that almost all updater at the hidden layer is very small. So this is the effect of using the sigmoid function, and it's very bad. Why is very bad? This is what we call as a vanishing gradient. Okay, you updating the updating the output layer in using a very big value, a very big updater value, but you are updating the hidden layer with a very small updater value. So that will make, actually this is what we call as a vanishing gradient condition, where if you have a small updater at the hidden layer side, that's mean as compared to output layer side, that's mean the learning process at the output layer is faster than the learning process at the hidden layer. Okay, hidden layer is very small, the learning process is very small because because of the updater value is very small. So this is not good, because in general, okay, normally the layer which is close to the input layer should be should update should need to be updated very fast as compared to the last one, because in reality you can see that let's discuss about okay, this is the pictures. Okay, if this W over here update very slow as compared to this one, actually it's not it's not good for your algorithms. Imagine that if you talk about some neural network which consists of more than one hidden layer, let's say 2 hidden layer, 3 hidden layer. So meaning that the more hidden layer you have, the smallest the updater will be. So if you apply the backpropagation for multiple hidden layer, then the one that close to the input layer will update very slow. But so that is not good for your network, because because in general this the first hidden layer which is close to input layer can consider as a frontliner. Okay, because in this day we talk about the frontliner. Okay, the term is frontliner for the COVID and so on, so I use the term for frontliner as well. So normally the frontliner here should become a good filter. It should be, the W here should be should be the good W that can filter out any unnecessary information and only pass the meaningful information to the other layers, because other layers is depend on the frontliner to filter out all the information and remove all the noise. So that's why if your learning process make the frontliner update very slow, then it's not good for your algorithm to find the very to achieve a converge towards converge and find the optimum W, which is the best in representing your learning algorithms or learning neural networks. So that is the disadvantage of gradient descent. But of course, even that's why you can see that when we discuss about gradient descent, we end up until we have only the example where you have only one hidden layer. We don't discuss the architecture which is more than one hidden layer, because otherwise it will be more and more suffer if you are using the gradient descent as the seed mod function as the activation function, because the more hidden layer you have, the smaller the updater it be. The smaller updater, especially the one that is close to the input layer. So that's why it's bad for your learning algorithm. So that's why the seed mod function only limited for this kind of version where you have one input layer, one output layer, and one hidden layer. Okay, then people try to improve this activation function. They propose this tangent function. Okay, the hyperbolic tangent function. Actually, the hyperbolic tangent function, disadvantage of this function is almost similar with this one. The one that improve is just the range there. You can see that this one, the range is from 0 to 1, but this one you have a wider range for -1 to 0. That is just the once you do that, then you will have a big value on this one. meaning that you have a big value but still suffer also with this vanishing gradient, just a little bit better than sigmoid, but still you suffer with vanishing gradients. Okay, and the after that, when they talk about, after that they try to improve this one, and then they try the most recent activation function is called ReLU. Okay, ReLU, rectifier linear unit function. This is the one that have been used in deep neural network. Okay, because so you can see that why is this one have been used, because now you will have the value of this one, the value of derivative of ReLU is bigger, so the updater become bigger and bigger, then it will solve the problem of vanishing gradient. And why this one is become popular right now, because again, when we talk about deep neural network, actually if you have a more and more hidden layer, so once you have more and more hidden layer, that's why before we introduce with the deep learning, okay, this one become popular, because we talk about only one hidden layer. But when we have the era of deep learning, what is meaning by deep learning is one of the characteristic of deep learning is that you have more and more hidden layer, so this activation function is not relevant anymore. So now the one which is suitable to be used for deep learning is ReLU, which is can solve the problem of the vanishing gradient here, because the updaters there is very big, so doesn't matter you put many value, I mean many hidden layers, you still the hidden layer which is close to the input layer will not suffer with vanishing gradient, because the updater or the derivative of ReLU is very big, which is the blue ones. Okay, just that. Okay, and some of it try to improve the ReLU, because ReLU still have this disadvantage on the negative side, because it's 0. Then some people try to introduce with this leaky ReLU functions. Okay, so because they want to have the negative value not to be 0 during the derivation. So then even it means that if you have the case where you have the negative value, still the process, the information is passed through the network. Otherwise, if you have this kind of version, if you have a negative value, then you don't pass the value, the information, the negative value to the other layer, because anything negative you will set as a 0. So that's why they introduced with leaky ReLU function. Okay, so again, and softmax function have discussed before, even during the earlier lectures. Okay, it's for multi-classification. So that is related to the activation function, and I think I don't have to discuss this one anymore later in deep learning chapter, because it's represent the same things. Even later you will have the slide there, the slide of introduction to deep learning, and the next lecture slide will also have activation function part, but I will skip that because we already discussed in these lectures.